January 2032. On the rim of a crater near the moon's south pole, sunlight that has taken barely a second and a half to cross the void strikes a cluster of silver domes, half buried in gray dust. Inside, the air is warm, the lights are on, and a crew wakes up for another day of work on another world. No science fiction, no CGI, a real address with real people, permanently living beyond Earth for the first time in human history. It's a stunning image. And the question this video wants to sit with is simple and a little uncomfortable. Could NASA actually pull this off in the next 6 years? Not a flag and footprints visit like Apollo, not a few days of camping in a lander, but an actual functioning outpost, something you could reasonably start calling a moon city, up and running by 2032. To answer that, we need to look at what NASA is actually building right now, what the moon itself will demand of anyone who tries to live there, and where the gap sits between an exciting headline and lunar reality. Let's start with where things really stand, because the truth is stranger and more interesting than most people realize. For most of the last decade, returning to the moon has felt like a promise perpetually 5 years away. NASA's Artemis program launched its first mission back in November 2022, an uncrewed test flight that sent the Orion capsule on a loop around the moon and back. It worked beautifully, but everything after that has been a story of ambition, running into the hard physics and harder bureaucracy of actually building space hardware. The first crewed flight, Artemis II, was supposed to fly in 2024. It didn't launch until 2026, delayed by battery problems and issues with the life support systems designed to keep astronauts breathing safely on a 10-day trip around the moon and back. When it finally did fly, in the spring of 2026, it carried 4 astronauts farther from Earth than any humans in history had ever traveled, completing a crewed test flight beyond the moon in early April. That mission, importantly, didn't land. No lunar module touched the surface. It was a shakedown cruise, proving that the giant rocket in the capsule could safely carry a crew. The actual landing, humanity's first return to the lunar surface since 1972, has been shuffled around so many times that NASA eventually did something unusual. It renamed the mission. What used to be called Artemis III, originally targeted for a landing as early as 2025, has effectively been folded into what is now called Artemis IV, with NASA aiming for touchdown by 2028, and internal statements suggesting the agency is even pursuing the possibility of 2 separate moon landings that same year. Independent government oversight, for what it's worth, has already expressed real doubt about whether even that revised timeline is achievable, citing the ordinary friction of building a completely new class of spacecraft under enormous public scrutiny. So, before we even get to living on the moon, we have to be honest that boots on the ground, Apollo-style landing hasn't happened yet in this new era, and it's realistically at least 2 years out from where we stand today. And yet, something quietly remarkable happened in 2026 that changes the shape of this whole conversation. NASA stopped talking only about visiting the moon and started talking, very specifically, about building on it. In the spring of that year, at an event NASA itself began calling Ignition, the agency laid out a 3-phase roadmap for what it now officially refers to as the moon base. Then, in late May 2026, NASA held a follow-up event at its Washington headquarters where it turned the vision into contracts. Real money, real companies, real hardware. NASA Administrator Jared Isaacman stood in front of reporters and called it, in his words, America's and humanity's first outpost on another celestial world. Nearly $1 billion in new contracts went out that day alone, on top of earlier awards, to a set of companies most people outside the space industry have never heard of: Blue Origin, Astrobotic, Intuitive Machines, Astrolab, Lunar Outpost, and Firefly Aerospace. Between them, they're building robotic landers, cargo landers, crewed lunar rovers, essentially moon buggies, and small hopping drones designed to scout terrain before any human ever sets foot there. This is worth pausing on because it's a genuinely different strategy than Apollo. Apollo is a sprint. Get there first, plant a flag, come home, win the political race. What NASA is describing now is closer to laying railroad track before the train arrives. The plan, as described by NASA's own program leadership, breaks into phases. The first phase is expected to run through 2028 and cost around $10 billion, focused on robotic precursor missions. Landers and rovers scouting the lunar south. Pole, testing how spacecraft engines kick up surface dust, mapping hazards, and quite literally, walking the terrain robots will one day drive across. Only in the phases after that, stretching into the 2030s, does NASA's own roadmap talk about the thing people actually picture when they hear Moon City: pressurized habitats astronauts could live inside, and power generators capable of running a base through the brutal lunar night. In other words, NASA's own internal planning treats 2032 not as the year a city exists, but as somewhere in the middle of the runway, well before the plane is airborne. So why the moon's south pole specifically? Why not somewhere flatter, sunnier, easier? The answer comes down to one substance that changes everything about long-term survival there: water. Deep inside certain craters near the South Pole, sunlight never reaches the floor. These are called permanently shadowed regions, and some of them have sat in absolute darkness at temperatures colder than the surface of Pluto for billions of years. Orbital instruments have detected strong evidence of water ice trapped in that darkness. Not puddles or lakes, but ice mixed into the regolith, the fines, that sharp lunar soil that covers the moon's surface. That ice is the reason the South Pole has become the single most contested piece of celestial real estate in the solar system. Water means drinking water for a crew. Split it apart with electricity, and it becomes breathable oxygen and hydrogen fuel. The same fuel that powers rockets. A source of water at the South Pole means a base there. It doesn't have to ship every drop of water and every breath of oxygen from Earth, which is precisely why NASA's Blue Origin lander missions and its long-term base plans are aimed squarely at that region, described plainly as being home to stores of water ice, which can be converted to rocket fuel or drinking water. This idea, using what's already there instead of hauling everything from Earth, has a name in the space industry: in situ resource utilization, or ISRU. It sounds bureaucratic, but it might be the single most important concept standing between a few tents on the moon and an actual permanent settlement. Every kilogram launched from Earth costs an enormous amount of money. And rocket fuel, so any material a crew can pull directly out of the lunar ground, is, in effect, free once the equipment to process it exists. And it turns out lunar regolith is remarkably useful stuff. Engineers have been experimenting for years with sintering it, essentially melting or fusing the loose lunar dust into solid material using concentrated sunlight, microwaves, or lasers, and 3D, printing it into shapes: landing pads, roads, blast walls to protect a base from the spray of debris kicked up by descending rockets, and eventually the outer shells of habitats themselves. NASA has already tested versions of this technology on Earth, and even flown experiments simulating lunar gravity to see how loose regolith behaves when it isn't held down by Earth's stronger pull. The vision architects describe is one where a base grows in stages. Astronauts first live inside small, mobile, pressurized modules they bring with them, and only later does regolith get piled, printed, and sintered around fixed structures to turn them into something more permanent and far better protected. That protection matters more than almost anything else because the moon is an extraordinarily hostile place to keep a human body alive for months or years at a time. Earth has two enormous invisible shields most people never think about: a thick atmosphere and a global magnetic field, both of which deflect the majority of dangerous radiation coming from deep space and from the sun. The moon has neither. Its surface is bathed directly in galactic cosmic rays, high-energy particles from exploded stars and other violent cosmic events, and, far more dangerous in the short term, unpredictable bursts of solar energetic particles thrown off during solar storms, which can deliver a harmful dose of radiation in a matter of hours. Living on the moon, long-term without protection, isn't really an option. This is where regolith earns its keep again. Recent research modeling how lunar soil interacts with radiation has found that even a layer, just a few tens of grams per square centimeter thick, roughly comparable to burying a habitat, under less than a meter of lunar dirt, can substantially reduce the radiation dose that reaches astronauts inside. Piling regolith over and around a habitat isn't just convenient because it's free material sitting right outside the front door. It may be the only practical way to keep a crew safe over the kind of multi-year timescales a real settlement would require. Radiation isn't the only environmental nightmare designers have to solve. There's also the matter of time itself, or more specifically, how the moon experiences it. Because the moon rotates so slowly relative to the sun, a single lunar day and a single lunar night each last about 14 Earth days. 2 straight weeks of blazing, unfiltered sunlight, followed by 2 straight weeks of absolute darkness and cold, plunging to more than 100 degrees Celsius below zero. Solar power, humanity's go-to clean energy source, becomes a serious liability under those conditions. Panels that work brilliantly for 2 weeks go completely dark for the next 2, unless a base has some other way to store or generate power through the long lunar night. Even robotic missions run into this directly. The small hopping drones NASA is sending as part of its precursor moon-based missions are only expected to operate during the roughly 14-day lunar day, because when the 2-week lunar night arrives, their fuel simply freezes solid. For a handful of robots, that's a limitation you can plan around. For a permanent human settlement, it's an existential problem, which is why NASA has been racing to fast-track a different kind of power source entirely: a small nuclear fission reactor, roughly the size of a shipping container's inner workings, designed to keep running through darkness, dust storms, and anything else the moon throws at it. NASA's own reporting on the effort describes an accelerated push toward a 100-kilowatt reactor design the agency hopes to have ready for launch by around 2030, a notable jump up from earlier, smaller reactor concepts. Now here's where the story gets a little more complicated and a lot more human, because building a moon base isn't happening in a vacuum. Geopolitically, or literally, NASA isn't the only organization with its eyes on that same patch of lunar South Pole. China and Russia have their own joint roadmap called the International Lunar Research Station, and they have been remarkably specific about their ambitions. Their plan describes construction running through the second half of this decade and into the mid-2030s, with an operational phase intended to begin from around 2036. And Chinese officials have laid out a two-stage vision where a basic research station near the South Pole is completed by 2035, followed by a far larger extended model by roughly 2050. China has also stated a goal of landing its own astronauts on the lunar surface for the first time by 2030. And both nations have signed agreements to jointly develop a nuclear reactor to power their station. One report describing a target of having it ready by 2036. None of this is happening in isolation from NASA's own choices. Reporting on NASA's accelerated reactor program has explicitly framed it as a response to the risk that whoever lands a working power source at a strategic lunar location first could effectively establish a kind of keep-out zone, limiting other nations' access to the most valuable resources nearby. Whether you find that framing exciting or unsettling, it's a real driver behind why the pace of lunar planning has picked up so sharply in just the last couple of years. This isn't only a scientific project anymore, it's also a quiet, high-stakes competition over who writes the rules for how humanity occupies its nearest neighbor in space. So let's return to the actual question. A moon city by 2032. Could it happen? Independent assessments that have looked closely at every piece of this puzzle, the landers, the rovers, the reactors, the radiation shielding, the sheer complexity of keeping humans alive, through 14 days of lunar night twice a month, forever, tend to land in a similar place. Multiple analyses of the current pace of lunar-based development suggest that a truly continuously inhabited lunar outpost is more realistically expected sometime in the late 2030s or even the 2040s, with NASA's own foundational surface infrastructure landing in the late 2020s and early 2030s, and China's comparable infrastructure arriving on a similar timescale. That doesn't mean 2032 is meaningless as a marker. By then, if everything on NASA's current roadmap holds, and given the program's history, that's a genuinely big if, we could plausibly see the first robotic outposts fully established, crewed rovers driving astronauts across the regolith during short-duration surface, missions, oxygen extraction demonstrations running on real lunar soil instead of simulants back on Earth, and perhaps even a small nuclear reactor humming away, quietly proving that power through the lunar night is solvable. That's an extraordinary amount of progress, and it would represent one of the most significant expansions of human reach in history. But a city, something with the permanence, self-sufficiency, and population implied by that word, that's very likely still a decade or more beyond 2032, based on everything both NASA and its international competitors are telling us about their own plans. It's worth sitting with why that gap exists, because it isn't really about a lack of imagination or a lack of good engineering. Ideas. Almost every piece of technology this video has described, regolith 3D printing, oxygen extraction from lunar soil, compact fission reactors, radiation shielding habitat designs, already exists in some working form, tested on Earth or in orbit. The real bottleneck is the unglamorous stuff, funding that survives multiple election cycles and shifting political priorities, supply chains for hardware that has never flown before, and the sheer unforgiving standard required when a single mistake can end a human life hundreds of thousands of kilometers from the nearest hospital. The Artemis program's own history, years of schedule slips, a landing mission that got renamed and pushed back more than once, a major commercial partner's rocket exploding on the launch pad in the middle of this very moon-based rollout, is a pretty clear demonstration that lunar engineering has a way of humbling even the most confident timelines. And yet, step back far enough, and even this delayed, over-budget, politically tangled version of the story is staggering. We are a species that, just over 60 years ago, watched its first satellite blink across the night sky, and wondered if it was even possible to leave the ground. Now we are seriously debating not whether humans can walk on another world, but how quickly we can build permanent infrastructure there, nuclear reactors, 3D printed buildings, self-sustaining oxygen supplies, on a body that sits, on average, about 384,000 kilometers from home. For context, that's a little less than the distance you'd travel if you drove around the Earth's equator nearly 10 times, except this journey happens through an airless vacuum, at speeds measured in kilometers per second, ending on a world with no breathable air, no protective magnetic field, and temperature swings that would kill an unprotected human within minutes. That we're arguing about whether a permanent settlement arrives in 2032 or 2038, rather than whether it's possible at all, says something remarkable about how far the conversation has already moved. There's also something worth noticing in how quietly ambitious this new phase of lunar exploration really is compared to Apollo. Apollo was built to prove a point, and then, in a sense, it stopped. The program ended, funding dried up, and humans didn't return to the lunar surface for over 50 years. What's being built now, however slowly, however imperfectly, is explicitly designed not to stop. Robotic landers scouting terrain before crews ever arrive. Rovers built to survive years, not days. Reactors engineered to outlast the lunar night indefinitely, not just once. Regolith itself becoming a building material rather than an obstacle. It's a fundamentally different philosophy. Not a visit, but a foothold. So maybe the honest answer to what if NASA built a moon city by 2032 isn't a simple yes or no. Maybe it's this. By 2032, the pieces of that city will very likely be scattered across the lunar South Pole. A reactor here, a habitat module there, a rover kicking up dust on a ridge overlooking a crater that has sat in darkness since before life existed on Earth, waiting to be assembled, into something people a few years later might finally be comfortable calling a city. The countdown isn't really to a single dramatic ribbon-cutting moment. It's to a slow, stubborn accumulation of small, unglamorous victories. A reactor that survives its first lunar night. A 3D printer that successfully seals its first regolith wall. A crew that steps outside a real permanent shelter instead of a temporary lander for the first time. When that day eventually comes, 2032, 2036, or later, it won't just mark the birth of a base on another world. It will mark the moment humanity quietly stopped visiting the moon and started for the first time in its history actually living there.